the Graz University of Technology. Daniel works on the solution of inverse problems within the Bayesian framework by using different sampling approaches and also reduced models. And he has always been very involved with works related to the automotive industry in Austria.
True, yeah.
So it's a great pleasure to have you here, Daniel. You have the floor.
Yeah, Helcio, thank you. Thank you very much for these kind words. And first of all, thank you very much for inviting me. Thanks to Marcelo as well. It's always a pleasure to come to Rio de Janeiro, especially at those days, at those period of the year. And it's quite nice to see that during this conference, the pure mathematicians work together with the engineers. So hopefully we can learn from each other, at least when it comes to applications. And it's great to see that things like that happen. So I will basically talk today about statistical modeling and Bayesian inference especially for two different industrial applications. I'm basically with the Institute of Automation and Control at Graz University of Technology, and also scientific director of the so-called Virtual Vehicle Research Center. That's a research center which is partly owned by the university and partly owned by the Austrian local industry, which is more or less automotive industry. That means Magnus Steyr, for instance, or AVL or Siemens are more or less pushing and supporting this research center, and that's the name, Virtual Vehicle, which actually was planned in the beginning of the century to mainly work on applied topics in simulation. That's why virtual vehicle, to make this virtual world, let's say the virtual twin, the digital twin happen of a car or a truck or even a train. And yeah, today I would like to split the talk a bit. The first part would be focused on one imaging technology, especially electrical capacitance tomography, ECT. That will be the first part. I will try to give you a certain motivation why we are still working on this very important topic. And we are quite happy that the Austrian industry has already taken over some parts of those ideas. I will give you a bit of more insight what we are doing in terms of solving the inverse problem, the underlying inverse problem, using statistical approaches. And the second part will be a bit more focused on, let's say, on a very hot topic over the last 10 years. Lithium ion batteries are well known in laptops, well known in our mobile phones. And meanwhile, they are in the series cars. When you buy an electric car or a hybrid car, you actually buy or at least lease a lithium-ion battery. And I will show you a bit the main issues. We are still struggling with it, although the technology and the electrochemistry behind is well known meanwhile, but finding a proper model for it and predicting the lifetime of such a battery is still a big issue. So when we first part, when we talk about ECT, we basically talk about imaging non-conducting materials. The oil industry in the early days was quite interested in imaging different phases, 2 phases or 3 phases, which usually are oil, some gas or water or mud. So you have different phases, and taking probes downhole is just too expensive. Having one sensor and measuring around this tube and getting inside in order to more or less have a kind of termination. Does it make sense to convey oil further, or should we stop because the quality has decreased that much? Is quite a cost issue for the oil industry. And the electric way is rather cheap. So if you use just electrodes around the pipe instead of other, let's say, more expensive equipment, like we heard already today. If we talk about terahertz, then the measurement equipment gets quite expensive, and for mass production, at the moment it's still an issue. Within such a pipe, we have non-conducting material. We actually are interested in imaging the permittivity inside. Permittivity, just to give you an idea, the lower bound is by definition 1, so that's what physics is telling us. Oil is, let's say crude oil is in the range of 2 to 3. Water is somewhere 80 to 80, 85, 87. And gas, of course, is close to 1.1. If we, let's say, first have a step before we talk about the maths behind, about the equipment, because I would like to motivate it from the application side. We basically need to measure the voltage around our pipe from the different electrodes, which are typically 12 up to 16 electrodes. That's quite common sense. Meanwhile, we have, let's say, we have to put quite a lot of constraints and requirements on our electronics. And one of the main issues is that we have to resolve capacitances in a very small range. We are talking about femtofarads and picofarads, while given stray capacitances in a much higher order. So that's quite a difficult thing from the application point of view, from the electronics. Then, of course, we need a high dynamic range. What I mentioned before is that we have to cover permittivities from 1 up to 90, for instance. That means we need a dynamic range there. Of course, we would like to have a measurement resolution which is quite high, which hopefully helps us later on in the reconstruction, that we also can come up with a resolution which is also quite high. But usually, and you might know if you're dealing with electrical tomography, independent of its EIT or ERT or ECT, usually we are talking about 5% image resolution. Let's say 2 to 5%. 2 is already a good value. And that's just one picture showing the implemented sensor as it's already now in place in the industry, where we actually have 16 electrodes. Our carrier frequency is 40 megahertz. We have this previously mentioned range of let's say the quantities of the measured capacitances, and about 100 hertz, which we can provide to the, let's say, to the signal processing, the analog digital, and later on the reconstruction procedure. And that's a typical trace of a measurement setup coming out. First thing, of course, is before we talk about the reconstruction, we have to model the physics. Anyway, we can follow 2 approaches. We can use the finite element method or the boundary element method. Just very quickly, the basic, or let's say the governing equations are, of course, Maxwell's law for, let's say, for the quasi-static case. So here we have the Maxwell law, and if we, let's say, if we neglect the internal charges, we can come up with this set of equations with those boundary conditions. And in fact, the measurement procedure is that way, that in any single, let's say, measurement step, we have one electrode active with 3.3 volts. All other electrodes, the other 15 remaining electrodes, they are grounded. That means here we have a 0 potential, and that's one measurement. Then we just switch to the next electrode, and we make it one turn around, and then we have our, let's say, our set of measurements, which can be used for the reconstruction. That's our measurement data. Yeah. And just a short look, the first idea is, of course, to use the finite element method, which is, I think, the typical way of modeling such a sensor. And there, I think, since let's say the 90s, a lot of imaging papers can be found which use the finite element methods for any reconstruction, whatever you want to use afterwards. Of course, one thing to mention is the discretization error, which is still there. And in fact, of course, you can do the brute force, make the triangles as small as possible, but you have to take into account the measurement noise, which is there, and at a certain stage. So there's a trade-off between the measurement noise and the discretization error. And at a certain stage, if you're below the measurement noise in the error, it doesn't make sense to increase the number of finite elements, because the measurement noise is canceling out this effect that you're thinking that you're getting better, but in fact the measurement noise is your lower bound. And for the previous mentioned setup, we are actually measuring and using the charge. So it's based on measuring the displacement currents. And basically, we are integrating the charges out of it, and they are used for the reconstruction. If we follow the different approach, instead of finite elements, we can also go for the boundary elements. If we, let's say, depending on the application, if we see that we have piecewise constant elements inside, that means we can assume that epsilon 1 is, for instance, that's all of this white region is water, the black region or the dark gray region is oil, and we are piecewise constant. We can actually go for the boundary element equation, and the other, let's say, benefit is if we are interested in recovering the contour, so let's say the shape of the inclusion, then it makes sense to go for the boundary element equation, where we then come up with the system of linear equations with the so-called influence matrices. The next thing, which is quite important, if we have on the one side our measurement equipment, on the other side our reconstruction setup, that means our simulation world, we have to figure out, we have to calibrate our model. That's typically, I know it's an engineering word, but for a certain stage, we have to come up with a match of the virtual world and the real world. And we have to work out, and usually you do it like this. You calibrate your model, or you fit your model, so it's more or less an optimization task for an empty tube and an empty simulated environment, and then you define a certain phantom, like a centered circle or two circles in there, and you, let's say, you fit the data, your model, exactly to this new, let's say, internal setup. And then you hopefully come up with something like that your, let's say, your model error is Gaussian distributed, like in that case. That's the perfect setup, because then you can later on assume that you have Gaussian distributed noise. The other thing, which is quite important, instead of adding some, let's say, synthetic noise data, if you have a real setup, then you, of course, have to work out the noise model. That means you define a certain material distribution and you sample from your measurement setup. So you sample, for instance, 10,000 repeated measurements, and you work out the noise distribution. In that case, we see that we are, let's say, in that region, we are quite good or well distributed in the Gaussian white noise. But to the tails, we are let's say, we are losing this Gaussian distribution, which is actually, so we have to work out if we should consider that or not for our reconstruction process. In fact, let's say the explanation why we have this kind of setup is that there is a certain crosstalk between the electrodes, and we are, let's say, deviating. We have a certain deviation from this, let's say, optimal white Gaussian noise. That's the correlation coefficient also worked out from the measurements. Basically, we can now think about, so we have the data, we have the ingredients, so we have the model calibrated, we have the noise model worked out. Now we can think about how to work out the, let's say, the inverse problem, how to get it solved. There are many approaches around. We heard a lot about yesterday and today about, let's say, regularized methods, which are really well known, which are working quite well for many situations. And of course, there are some drawbacks, but in fact, you can also go for statistical inversion, let's say the full MCMC approach, or if you are interested in a time variant problem, if you would like to track the material distribution over time, then you basically should go for, let's say, for recursive filtering, like the Kalman filter or its modifications, or the particle filter. Or I will show you pretty short later on the H-infinity filter, which also is a nice alternative if you would like to cover both model noise and measurement noise. What we know so far is that for classical deterministic methods like regularized solutions, so without, let's say, to generalize it too much, but in certain situations, we have problems if we go for the classical regularized method. If we have large noise cases, so the measurement noise is quite high. If we have, let's say, very bad models, or even if you have time-varying problems, then it might make sense to think about statistical methods with a couple of, let's say, benefits, advantages, like those that we can more or less, in the end, we have a posterior distribution where we can calculate any statistics we're interested in. So we are not having one single mode, one single result. We have more or less a sample set where we can calculate marginal densities out of it. We can calculate conditional means. Even the maximum likelihood or other modes can be worked out of this posterior distribution. And of course, the prior knowledge is quite important and easy to, let's say, or intuitively to integrate in a Bayesian framework. Of course, in the deterministic way, you're also dealing with prior knowledges in a different way. Yeah, and the other thing is, I mentioned right before, if you talk about non-stationary problems, you usually, it's quite an intuitive way to go for the extended Kalman filter or other approaches. Just to make it a bit more clear, so just opening the entire slide, it's a bit hard to see, but there should be a gray region around. If we just, let's say, match between the image space and the measurement space, you usually have more or less your dependency through the forward map between those two spaces. And the main issue is in the measurement space, you don't have the ideal measurements. Usually you have some let's say, noise vector pointing to this set. The set is let's say, the measurement corrupted by noise. And if you then solve the inverse problem, you're ending up, for instance, if you go for the maximum likelihood, you end up here while the true distribution or the true parameter set is different to the estimated one due to the fact that we have to deal with noise. And of course, we would like to see some sort of unbiased behavior and in the perfect way, zero mean noise, because then we can work out this issue, what we're having here. And the Bayesian framework actually provides the setup that you can combine the likelihood function, so the measurements, with some sort of prior distribution, which is usually constructed before you do any measurements. You need the physics model and, of course, the noise model. Then you actually can apply Bayes' law. And given that, we also have to consider a few other things. That's a bit picture what I actually like from the signal processing world coming, that we have some sort of, let's say, analog digital converter inside in our chain, so we have a data loss there. We have the noise term, so depending on our instrumentation, we have some additive noise, and basically this entire chain has to be considered also as prior knowledge, so we can include those parts as prior knowledge in order to bring in some sort of intelligence to work out the parameters of interest, the unknowns in tomography, actually, let's say, parameters that describe my material distribution, so the permittivities inside. The prior itself can be done in different ways, so we can talk about low-level, mid-level, or even high-level priors, depending on what you're interested in the reconstruction task. So it's actually depending on the application, more or less. Let's say usually, or in that case, we applied the classical MCMC, Markov chain Monte Carlo, with Metropolis Hastings green dynamics. So exactly that way, where you also have the gradient computed there. It's much easier to implement on the computer, but in fact, it's the classical way, and it's definitely not, let's say, not the rocket science to implement the MCMC. More interesting is how to construct this so let's say to propose the new candidate in your Markov chain to the next step for that special case in monitoring, or let's say in recovering the shape of a single inclusion. It actually makes sense to go for different moves, which are chosen randomly. So you pick different moves by random, so some sort of translation, so moving around in X and Y in the plane. A vertex move means just moving one single control point. A scaling move, so scaling and shrinking, and the rotation move, of course. So you pick those at random. You choose a step size at random, so a lot of random parts are in there, but that's the behavior of an MCMC. And once we are sampling from the target distribution, that means if the MCMC is constructed properly and if everything is, let's say, running well, then basically at a certain burn-in phase, we are sampling from the equilibrium distribution, from the target distribution, and it's independent from the initial state. That's the good thing. If the MCMC is constructed right, you can start wherever you want. You finally sample from your equilibrium distribution, from your target distribution. And in order to work out and to quantify the uncertainties, you usually you go for plotting all the histograms for the parameters of interest, like here, the circumference of the inclusion or the area of the inclusion. You can more or less work out the so-called integrated autocorrelation time, which gives you a bit of statistical efficiency. So it's a measure for statistical efficiency, and the faster this decay is, the better is your Markov chain mixing up the updates, generating less uncorrelated samples. Or just a different example, just go quicker above over those plots. Then the good thing is if you do Markov chain Monte Carlo sampling, that you instead of or let's start in a different way. If you usually start in a deterministic case with regularization with an L2 norm, you have some sort of smoothness assumption. You more or less penalize your entire reconstruction task, or you predefine a certain way of what you would like to see. And if you use MCMC, of course, the down cost is the computational effort, the time. You can also work out high-frequency parts in your contour, which is a bit easier to work out. And the nice thing, what I always like, is that you get these nice scatter plots that show you the variance of the reconstructed data. Because let's say, as a measurement engineer, as a signal processing engineer, I'm usually like to say, whenever you have measurements, you have statistics. Measurement is always like statistics, and once you have statistics, you have to deal with stochastic processes, and that means there is not only one single solution, there's always a range of feasible solutions, depending on, or given, or predefined due to the stochastic process driven by the measurements. And as smaller the variance, the better is, of course, our estimator, our reconstruction result. And the MCMC actually is telling you clearly, if you have lousy measurement data, then you can't do it with signal processing, because the data is bad, is lousy, and the MCMC is definitely telling you that the data is lousy, and you might spend some efforts in the sensors, in the measurement setup, in acquiring the data. Here, there are some other traces which are usually used in order to, let's say, to quantify the uncertainties and, in fact, to work out if the MCMC could be improved, could be optimized or not. You could even go for fill level sensing, and you also see the scatter blocks are showing the variance. So there are feasible fill levels at this level and also at this level, showing that the measurement data is just telling you that, and it can't be, you can, of course, calculate the conditional mean like here, but in fact, you have an upper and lower bound. If you would like to deal with the non-stationary problem, you basically should use filters which are, let's say, out of the Bayesian filter family. The most famous one is, of course, the Kalman filter with all its extension from the sigma point Kalman filter, particle filter, and so on. Basically, you need to set up a state space model. For that case, we would like, so our parameter of interest, in that case, we are talking about the finite element forward model. So our epsilon vector has a size of, let's say, 10,000 elements. In that range, so it's going to be a bit difficult. Usually, you have to include some sort of regularization. So here we are quite close to the deterministic case, and we are actually, the Hofmann filter is nothing else than a map estimator, so a minimum unbiased, minimum variance unbiased estimator, given certain assumptions, of course. But in fact, you can easily set up calculating in a numerical way the Jacobian matrix, augmenting the state space representation by the regularization elements, working out the alpha parameter, as we heard right before the coffee break. It's a bit of work. It's still not an obvious solved problem to work that out. The H infinity filter, just very quickly, is one let's say, one nice thing, which is maybe not often used, at least not in the engineering world. The H-infinity filter gives you both benefits. You deal with the measurement data, that's the one thing, like the Kalman filter. And the other thing is you can deal with a delta in your system dynamics matrix. That means you can actually have an A plus delta A. So you're optimizing more or less the worst case. So you're looking for, so you're optimizing, you're minimizing the worst case. So you are always on the safe side if you go for the H-infinity. It's a robust filter, a robust estimator. And for a certain, I think it's not that important to go through the equations. More important maybe is to see that if you look at this set of equations, they are pretty similar to the Kalman equations. The only difference is this factor theta. And if you set theta to 0, then those equations reduce exactly to the Kalman filter equations, to the well-known Kalman filter equations from the early 60s. And basically, it's an optimal filter like the Kalman filter, but just to recall, with the big benefit that you can deal with the system matrix and its, let's say, its process-dependent noise within the system dynamic matrix. So A plus delta A. Yeah, exactly. And that's just the way to reduce to the Kalman filter. And just for ECT, just one table where we compare the so-called void fraction. That means the fraction between the oil in the otherwise uniform background material, oil and water. And what you can see here for the specific example, the H-infinity filter is much better than the Kalman filter for this specific ECT application. And for this, let's say, for this parameter conditioned on the measurement data. So it's worth to try the H-infinity filter in that case. Yeah, so it's not a general statement that the H-infinity filter is always better for this specific application. It turned out that the H-infinity filter does make sense. Of course, it comes, again, with a bit more computational efforts compared to the Kalman filter. And the last, just to mention, the last part in this family, which is also quite often used, the particle filter, with the big benefit that you don't have to calculate the Jacobian. You can just sample from your nonlinear function. And you also, and that's the different to the H-infinity in the Kalman filter, you can deal with multimodal distributions. That means you can also reconstruct 2 or 3 inclusions within the pipe, and only one inclusion. If you would like to use the Kalman filter for 3 inclusions, you need 3 Kalman filters because they track just one part. And yeah, so basically you try to approximate your nonlinear function by a set of weighted particles or samples. And it looks like if you reconstruct, if you use the data, it looks like that. You spread the particle somewhere, and hopefully, if everything runs well, you get you collapse or you converge to the right shape and the right position, and also given some let's say some variance in the result, the posterior variability, which you can also use it like shown here for fill level sensing. So the particle filter is quite a nice thing, especially when you have nonlinear problems, and you're not able to calculate the first derivative of your function. Yeah. So in fact, if you talk just the sum up of the ECT part, statistical approaches, and let's say in the modeling part, are quite important, especially when you have a measurement set up. If you have the measurement set up, then you have to work out the noise model because you have the setup there, and you get the right noise. You can more or less model the noise, the right distribution. Maybe it's a Gibbs distribution. Not always. Unfortunately not always. It's a white Gaussian noise, a normal distribution. But in fact, you need to model the noise. You need to model, let's say, the difference between, let's say, the error, the model error between the real setup and your forward problem. And the good thing is you get more or less a range of parameters which fulfill the solution. That means you get a range of feasible solutions that solve your inverse problem. And you can calculate any statistics you want out of your result, out of the posterior distribution, and you can quantify uncertainties, which is quite important, especially when we talk about, let's say, things like the guide of uncertainty expression in measurement. Then you have to quantify, especially when you want, like, if the industry wants to sell measurement equipment, they have to quantify the result of such a system. So you saw another application I would like to tell you in the remaining time is a very popular topic over the last years, the lithium ion battery. And lithium ion batteries are, so just to motivate it a bit, there is not the only one lithium ion battery around which you can buy. We have to distinguish between different kinds of lithium ion battery. If you look inside the battery, we have different materials inside. We have, for instance, lithium iron phosphate, lithium carbide, lithium mangan. So a lot of different ways of building such a lithium ion battery with different goals behind. Because what we actually would like to have for an electric car is we would like to be there. So high power and high energy. High energy means range. High power means fast charge and discharge. And actually, we would like to have both. So if we are passing by on the highway, we would like to have, if we press the gas pedal, we would like to have, let's say, a good acceleration in order to pass by. On the other side, we would like to run for 1,000 kilometers or even more, like we have with diesel engines or gasoline engines. But in fact, we don't have this battery which fulfills both. So we have high energy batteries and high power batteries. And one of the big issues, or there are two big issues in battery research. Although it's already in serious production, but it's still not solved, so you can't buy cars that run for 1,000 kilometers. And you always have to, let's say, you have to spend a bit more money for electric cars compared to a conventional car. And one reason is the safety issues. It's still not solved that, unfortunately, let's say, in other way, unfortunately, the safe batteries are the more expensive batteries, and those batteries don't have the range, so they have a low energy density that makes them not very useful at the moment, so there is still research required. And the other thing is the aging of the battery. That means batteries are aging. Lithium-ion batteries, unfortunately, are aging. We don't really consider that for our mobiles and our laptops because we usually change our devices every 3 years. So we do not care about that. But for the automotive industry, it should work for 5 up to 8 years so that you don't have to change your batteries because it's a bit more of effort due to the active cooling and all the other things. Basically, we have like every battery, there is a cathode, an anode, and we have some electrolyte in between. And if you look a bit more inside, and the basic idea is we would like to model such a system because for predicting aging effects, predicting safety effects, because safety is always driven by some sort of thermal behavior, thermal changing. And that's why we would like to have, let's say, a comprehensive electrochemical model also representing the temperature behavior so that we can predict any situation we would like to predict. And as you could imagine, such a battery is a quite complex system, and we have to come up with some certain assumptions and definitions in order to succeed. Basically, if you look inside the structures, so that those are with a raster electronic microscope, you can come up with, let's say, that you more or less model the particles as spheres, for instance, that you predefine a homogeneous distribution, that you ignore certain things within the battery. And basically, we come up then to some sort of a basic model, and this model looks like this. So it's one of the things where I'm quite happy that people from Graz, Stefan Volkwein at those days, and also from the Kapel Institute helped us, because as engineers it's a heavy thing because you have partial differential equations coupled. You have the so-called Butler-Volmer equation with unknowns. So the green parts are the unknowns in the exponential function, and simulating the thing, this entire framework is a difficult thing in order not to exceed in time. Our first approach was that we let's say 1 second in real time was calculated over 1 week, and that's not feasible for the industry. And you have to think about that Volkswagen and Porsche are partners who are paying that, that they hopefully get a nice model to be used in their environment. Our first approach, of course, was to work out are all parameters, and we are talking about 70 parameters, are important, and we just did this very, let's say, engineering closed approach, the so-called factor fixing, more as one at a time, that you can work out the direct influence of parameters and the degree of nonlinearity, and you see that those parameters which are in that range or in that range should be considered more than those parameters which are here. So we are talking about diffusion coefficients, porosity coefficients, and so on. Then, of course, we have to define some certain, let's say, stress profile, which we got from the automotive industry. Let's say we start at a certain level, zero state of charge, then we charge, then we hold, then we have a rest time, discharge, hold voltage. So that's a profile which simulates a typical behavior in a car. And basically, the first approach, and it's 5 years in the past, or 4.5 years in the past, showed that we could work out first, let's say, inside the battery, where you can see the anode, the cathode, the potential there, let's say the concentration of the electrode, also of the cathode and the anode side and the cathode side, and the state of charge. So that was the first idea for highly dynamic pulses and also for rest times. So that was the first approach. Then, of course, we had to work out how to estimate the parameters in there. Of course, my approach would be the stochastic method, but it's really slow, and we decided to go for a gradient-based deterministic method, the so-called surrogate approach that is more or less, we are switching between a coarse and the fine model. So a so-called surrogate model-based optimization method, and it turned out that with this method, we actually could improve the computation time quite a lot. So we actually set up the fine model, the coarse model, and basically it turned out that given the coarse model, it was much easier and a lot faster that we switched between the models for certain with a certain procedure, of course, and basically it's just speed up a bit. We came to the conclusion that, or let's say we figured out that we could save in this first attempt 25%, which is a bit, but actually we are still too slow there. And next step we did was that we worked out the adjoint approach, which gave us, so we are talking about the electrochemical potential there. We have the simulation and the measurement. We worked out the adjoint model, and basically we just compared let's say the classical finite differences to the adjoint system problem, and those are quite, so that's the magenta and the orange one, are pretty close, a bit, let's say, lower than the target function, but they are quite well matching. If you look at the voltage, the cell voltage, that's quite fine there. And that gave us 80% even in the 3D case, which was a huge step forward for us, because then the battery was suddenly we could simulate it in a certain time. So basically, and just I think 4 minutes, something like that, in the next step, we of course had to work out the uncertainty of those parameters. So how can we trust those parameters? And of course, we decided to go for the MCMC. With the idea of working out the confidence, the uncertainty of the certain parameters we have more or less identified and estimated, and we decided to go for Metropolis Hastings sampling in the parallel adaptive scheme, which gives us a really great results. And just show you the different for different diffusion coefficients and the porosity coefficients, which are quite important, that we could actually work out with the parallel method with and without noise, and so with the single procedure in the MCMC, that we could actually see that the parallel case with noise could actually gives us more or less the range of parameters, which is quite important, and the parallel case with noise and no noise, it's independent, is of course the fastest way compared to the individual way to work out those uncertainties. that's not that important, basically, and that's maybe the closing the gap. Again, we are working out the integrated correlation time, which shows us that there is at least some need for improvement, because we are quite slowly in going down, and actually the Markov chain is not mixing very well at the moment, so there's still work to do in order to proceed with that. And one other thing, one other outlook is the aging effect, which is where we are currently working on. Aging is quite an important thing, and as you can see here, there are so many causes that accelerate aging of a lithium-ion battery, and the effects are just two. The power fade and the loss of capacity, which you can measure from the outside, and there are so many correlations in between that will give us a lot of work to do in order to parameterize our electrochemical model, to find the right parameters in there, to identify those parameters which are changing in a certain way, given that correlation, which is subject to work, because what you see here is that even for only for 550 and 300 cycles charging, discharging, the material is changing significantly within the battery, and you have to more or less model that in a mathematical way. You can see here another example that so for the first cycle, when we start with the cycling, charging, discharging, after 300 times charging, discharging, it looks like that, and we have to model that in a certain way. And that's basically, let's say, the outlook. We have to work together, and that's the good thing. Industry is paying quite a lot of money in Europe for working out that, let's say, an optimal electrochemical model which is able to predict safety features. That means to predict the temperature in a very accurate way, and also to predict certain, let's say, certain aging effects over time in order to figure out what happens with a certain stress profile, a certain load profile over the time when you cycle in a hybrid car, in an electric car, or even in different classes of cars. Let's say a small car, larger car, or a premium car. So that's the basic thing, and the most important last message is, of course, measurement is always there. Measurement means statistics, and if you have let's say the benefit to have the measurement set up, then please go for the noise model first, and then for the reconstruction or the parameter estimation approaches. Thanks for your attention.
Thanks very much.
And sorry for being a bit late.
No problem.